Chapter 11 gets into now liquids. We just transitioned from gases and we ended gases talking about how gases and the kinetic molecular theory breaks down, specifically under low temperatures when it gets cold and high pressures when they get squished together. Once that happens, something called intermolecular forces, or IMFs, start to take hold. Intermolecular forces are the attractions between molecules rather than within, and they are weaker than intramolecular forces. So inter means between, intra means within. So intramolecular forces are like what we have here, are bond. So bonding, covalent bonds are intramolecular forces. But what holds the molecules together, like when we're a liquid or a solid, is these weaker interactions, which are IMFs, or intermolecular forces. Most of the properties, physical properties of a compound are reflected by their intermolecular forces. So we have boiling point, melting point, viscosity, surface tension, and capillary action are all reflected by IMFs. And one thing we're going to do is use these properties. Oftentimes you'll see boiling point and melting point as a way to compare intermolecular forces. So let's discuss what an intramolecular force is. These are the chemical bonds. So we have, what you've already learned about, ionic bonds, like between a metal and a nonmetal. We have covalent bonds between nonmetals. This could be, we'll talk more about in the next chapter, covalent bonds that hold full solids together. And then metallic bonds are between metals. So we have metal plus nonmetal, just metals, and then just nonmetals, covalently bonded together. And these guys, when they're in the solid phase, they have extremely high melting points and boiling points, and that's a key indicator that we're dealing with breaking. When we melt or boil, we're breaking these chemical bonds, or these intramolecular forces. When we talk about intermolecular forces, the whole chapter we're dealing with now, we're dealing with nonmetals or molecular compounds, meaning two or more nonmetals, and they form an individual molecule. And that's different from up here because these solids form large, kind of think about a metal, lots and lots of atoms just alternating in all three directions. Same thing with ionic solids. We have a lattice structure, and diamond is covalently bonded carbon and all on a sp3 hybridized tetrahedral form. So covalent bonds in all directions. When we have molecules, we have a covalent bond between the atoms, but they're not connected to an infinite amount of other atoms. They're just an individual unit. So for example, nitrogen, N2, it is just one atom of nitrogen bonded with another atom of nitrogen. So we have the forces for these guys are dispersion forces, dipole-dipole, and hydrogen bonding, and they're going to have much lower melting points, and they vary depending on the type of IMF that we're dealing with. So the biggest difference between the states of matter is the strength of the IMFs of attraction. So how strongly these molecules or these particles are being held together. The stronger the force is, then that means the molecules are held even tighter, making it harder for them to break apart. The way that we can get them apart or to separate is by increasing the kinetic energy. That helps them to separate or keep them apart and moving. And the way that we do that is by adjusting the temperature. So as we increase the temperature, the kinetic energy goes up, because kinetic energy is 3/2 times the gas constant times the temperature. So as temperature goes up, our kinetic energy goes up, and we can get those particles to move around. They can go from the solid to the liquid if I heat it up, and if I heat liquids up even more, I can go into the gas phase because I'm heating up that kinetic, or increasing that kinetic energy. Here are just properties of liquids, solids, and gases, which you have probably already learned many times by now, but just as a recap. Gases expand to fill up their volume of and shape of their container. So they fill it all up, They can also be compressed. They flow because they have movement in all the directions. And they also diffuse very rapidly. Liquids, on the other hand, they can assume the shape of part of their container, but they don't expand to fill it. They don't really need compress because there's not a whole lot of room if we see in between the particles. They do flow though, right? If you spill water, it gets all over, versus if you spill ice, it doesn't get all over. It stays in place. And diffusion does happen, but it happens slower. So if you think about if you put some food dye in some water, it would diffuse, but not as fast as if you sprayed perfume and the perfume diffused across the room. That's a lot faster. Solids retain their own shape and volume, and they do not expand. They don't compress much. They don't flow, and there is very, very, very slow diffusion.